my name is Lexi and I'll be recording our lecture for today. So let's get right into it. So we are on covariance, so here we go. So variance describes how a random variable deviates from its mean. The covariance can describe the linear relationship between two random variables. So our definition of covariance is the following. So let x and y be random variables with a joint probability distribution f of x, y, and the expected values mu of x and mu of y. So then the covariance of x and y is given by the following equation below, formula. So covariance is equal to the expected value of x minus the expected value of x and y times y minus the expected value of y. And then if they're discrete, we can use our summations, and if they're continuous, we use integrals to get all of the values of x and y. And so covariance is used to describe the linear relationship between two random variables, but it's also possible for two variables, x and y, to have a nonlinear relationship where the covariance between them is 0. And so as with variance, we have another theorem that we can use to calculate covariance that's much simpler and easier to use. So it says that covariance of x and y is equal to the expected value of x and y minus the expected value of x times the expected value of y. And covariance can be written with the following notation, cov x and y. So let's just look at an example of calculating covariance. So the fraction of x male runners and the fraction of y female runners who compete in a certain marathon race are described by the joint density function below. So we can see that over here, and we wish to find the covariance of x and y. So first we need to find the marginal distribution of x. So we can do that by taking our function and solving the integral from 0 to x of with respect to y. And when we solve that, we get 4x to the third for the ranges of x being between 0 and 1. And then we can use that now to calculate our expected value. So we take our 4x to the third, multiply it by x, and find the integral from 0 to 1. And when we solve for that, we get 4 over 5. So next we need to find our marginal distribution of y. So we do the same exact thing except with y. So we do 8xy, and we find the integral from y to 1. And we find it with respect to x this time. And when we solve for that, we get 4y minus 4y to the third for values of y between 0 and 1. And we can then find our expected value of y, which is we just take our 4y minus 4y to the third, multiply it by y, and then find the integral from 0 to 1 with respect to dy. And we solve for that, and we can get 8 over 15. And then finally, we need to find our expected value of our joint density function xy. So what we do is we take our 8xy from our previous function, and then we just multiply it by x and y, and then we find our double integral of y to 1 with respect to x and 0 to 1 with respect to y. And when we solve that, we should get 4 over 9. And then now that we have all our values, we can go back to our theorem over here where our covariance is given by the expected value of xy minus our expected value of x times the expected value of y. And we can just plug that in over here. So we have our expected value of xy is 4 over 9, and then minus our expected value of x, which is 4 over 5, times our expected value of y, which is 8 over 15. And then when we calculate that all together, we get 4 over 225, which is our answer and is our covariance of x and y. So covariance is useful for finding a linear relationship between two variables, but it doesn't provide meaningful magnitude, since the magnitude of the covariance depends on the units used to measure both the random variable x and the random variable y and their distributions. So say if you have x that's measured in centimeters and you have your y measured in meters, you're not really going to get an accurate, your magnitude isn't really going to tell you much since they're different measurements. So that's why we have correlation coefficient. So our correlation coefficient solves that problem, and it's given by the formula below. So let x and y be random variables with the covariance, and then we have our standard deviations for x and y. So our correlation coefficient of x and y is given by the covariance of xy divided by the standard deviation of x times the standard deviation of y. And so let's just look at an example. So if we use our previous example, we found that covariance of x and y is equal to 4 over 225. And then now we can solve for our standard deviation of x and y. So we know from previously our formula for variance is equal to our expected value of x squared minus our expected value of x, and then we square that value. So then we can solve for our expected value of x squared. So we can solve for our expected value of x squared by using our marginal distribution all the way from our previous slide. So that's 4x to the third, and then instead of multiplying by x, we multiply by x squared here. So that's x to the fifth, and then we can solve our expected value by finding the integral from 0 to 1 with respect to x, and that equals 2 over 3. And then we can find our variance of x by subtract, so we can get our expected value of x squared minus our expected value of x, and then we square that afterwards. So that's our expected value of x squared is 2 over 3, which is over here, and then we have our expected value that we calculated previously is 4 over 5, and then we can square that, and then we get our variance here, which is 2 over 75, and then we can do the same thing with y. So we get our expected value of y squared. We take our value from previously, which should be over here. So we have 4y minus 4y to the third, and instead of just multiplying it by y, we multiply it by y squared. And then we calculate our integral from 0 to 1 with respect to y, and we get 1 over 3. And then we can calculate our variance of y, which is our expected value of y squared, so that's 1 over 3, minus our expected value of y that we calculated previously, and then we square that. So that's 8 over 15 squared, and we get our result, which is 11 over 225, and that is our variance of y. And then down here we just take the square root, because the standard deviation is the square root of the variance. Variance is the standard deviation squared, so we just take the square root to get our standard deviations, And so we have our covariance divided by our standard deviations of x times the standard deviation of y, and that gives us our result here, which is 4 over the square root of 66. And that is our correlation coefficient. So for any random variable x and y, our covariance will be between -1 and +1. And our correlation coefficient. Our correlation coefficient will be between -1 and 1, and when our correlation coefficients, the absolute value equals 1, only if there exists numbers a is not equal to 0 and b such that the probability of y equals ax plus b equals 1. And so the second property essentially means that when there's a linear relationship between x and y, then the correlation coefficient equals 1 if the slope of the line is positive, and -1 if it is negative, if the slope of the line is negative. Okay, so then now we can move on to means and variances of linear combinations of random variables. So we can go over some useful properties of the expected value and variance of linear combinations of random variables, and that can just help make our calculations a lot easier. So our first theorem says that if we want to calculate the expected value of ax plus b, where a and b are both constants, they're real numbers, then we can simply calculate the expected value of x times a plus b. So we can, as it's written here, you can essentially just calculate the expected value of x and then multiply it by the constant or add it to a constant, and that's the same thing as the expected value of a times x plus b. Our next theorem here is for calculating our expected value of two random variables. So if we're trying to calculate our expected value of x plus y, that is equal to the expected value of x plus the expected value of y. So an example is, so we're solving for the weekly demand of a certain drink in thousands of liters from a local chain of efficiency stores is a continuous random variable g of x equals x squared plus x minus 2, where x has the following density function, which is listed over here. And so we are interested in the expected weekly demand for the drink, and we calculated previously that, so this is our same problem. So we calculated previously that the expected value of x squared equals 17 over 6, and our expected value of x equals 5 over 3. And so we can solve, so if we want to solve for our expected value of x squared plus x minus 2, we can separate these into separate parts where we find the expected value of x squared plus the expected value of x minus the expected value of 2. And so we have our expected value of x squared here, so we can just plug that in. We have the expected value of x here, which is 5 over 3, and we can plug that in. And then the expected value of 2, when it's just a constant, is just 2, so we can just plug in 2. And we can solve for that a lot more easily, and we can get our answer, which is 5 over 2. Okay, and then another theorem is if x and y are two independent random variables, then the expected value of xy is equal to the expected value of x times the expected value of y. And you might be thinking, wait a second, in one of our previous formulas, we said that these were different. And this is only true if they are independent random variables and they have no relationship between each other, because in that case, then our covariance is equal to 0, And so this adds up with our previous formula where our covariance is equal to, all the way over here, our covariance is equal to our expected value of xy minus our expected value of x times our expected value of y. And so if they were independent, this would be 0 because these two would be the same. So this only applies if they are independent random variables. And then our next theorem is if x is a random variable and a and b are real numbers, then our variance of a times x plus b is equal to a squared times the variance of x. And then if we have x and y as two random variables and a, b, and c are all real numbers, then our variance of ax plus by plus c is equal to a squared times the variance of x plus b squared times the variance of y plus 2 times a times b times the covariance of x and y. Okay, and then we can just do an example of using these rules. So if x and y are random variables with the variances of x equals 2 and the variance of y equals 4, and the covariance of x, y is equal to -2, and we want to solve for the variance of the random variable z, which is equal to 2x minus 5y plus 1. So we can solve for our variance of z, which is equal to our variance of 2x minus 5y plus 1. And then we can use our formula from previously, where our variance of 2x, so that would just be 2 squared times our variance of x. So this is exactly from back here, so a squared, where a is 2, so we have 2 squared times our variance of x, and then we have b squared times our variance of y, and then over here we have 5 squared times our variance of y, and then we have our 2 times a times b times our covariance of x and y. So 2 times a is 2, b is 5, and then times our covariance of x and y. And notice that our constant doesn't affect anything. And so we can solve for that, and we get our result, which is our variance of z is 68. So if x and y are independent random variables, then our variance of ax plus by is equal to a squared plus our variance of x plus b squared times our variance of y. So this is because if x and y are independent variables, our covariance will be equal to 0. So all of this will be equal to 0. So if they're independent random variables, we can just ignore the covariance part. And we're going to be skipping this, I believe, and on to the next lecture slides. So we're back for the next part of the lecture that we will be discussing, and that will be common distributions. So here are some common discrete distributions. So we have first our Bernoulli distribution. So first, what is a Bernoulli trial? So a Bernoulli trial is an experiment with 2 and only 2 possible outcomes, which are labeled as success or failure. So a random variable x has a Bernoulli distribution, which is denoted by Bernoulli p distribution if for some p, so p, which is our probability of success, needs to be between 0 and 1. So we can have our values of x, so our outcome is either 0 or 1, and it's 1 with the probability p, and 0, so 1 is success, and then failure, which is 0, with the probability 1 minus p. And what we label as success and failure are subjective, but here we're just labeling them with x equals 1 is success and x equals 0 is failure. So our theorem for properties of a Bernoulli random variable. So if a Bernoulli distribution has our parameter p that's between 0 and 1, then our expected value is equal to p, and we can solve that using this over here. So basically, if we're getting our average, mean, expected value, all the same thing, so our probability of getting, so our two values that we can get are 0 or 1, and if we get a 0, that is, we multiply it by our probability of failure, so that's 1 minus p, and then since it's 0, it canceled itself out, and then our probability of success, so if our value is successful, we have x equals 1, and then we multiply that by our probability of success, which is p, so that gives us our expected value of p. And then our variance, so we can just use our variance formula again. So the expected value of x squared minus the expected value of x, and then we square that. So that is our variance. And so we have our expected value of x squared over here, which is, if we just square our x, so 0 squared is still 0, 1 squared is still 1, and then we subtract it by our expected value, which is up here, which is p squared, so then we get p times 1 minus p, and that is our variance. So an example of our Bernoulli distribution or Bernoulli random variable, so suppose we flip a coin one time. Let x equals 1 if the coin shows heads, and 0 otherwise. And then we can let y equals 1 if the coin shows tails, 0, and 0 otherwise. And so both x and y are Bernoulli random variables. We can choose the condition that counts as success, so for x it's heads and for y it's tails, and both are still valid Bernoulli random variables. And then if x has a Bernoulli distribution with parameter p, then 1 minus x is also a Bernoulli distribution with the parameter 1 minus p. So that's our example right here, where we have x is when heads is success, so that's when x equals 1, and then we have our opposite distribution where tails is success, and that's when y equals 1, so 1 minus x, and then our parameter, our probability of success is 1 minus p. Since it's a coin, it's still 50% for each, but if it was a different value, it would just be 1 minus p. So many experiments can be modeled as a sequence of Bernoulli trials called a Bernoulli process. So a Bernoulli process has 4 main properties. So first, an experiment needs to consist of repeated identical trials. And then second, each trial has 2 possible outcomes, and then we can classify them as success or failure. And the probability of success must be the same for each trial. And the trials have to be independent from each other, so a previous trial can't affect the next trial. So now we have binomial random variables. So Bernoulli random variables are when we have one trial. It's just like an example of one trial for our Bernoulli distributions, but our binomial random variables are if we have multiple trials, and then we have a distribution based on that. So let x1, x2, all the way to xn be independent and identically distributed Bernoulli random variables with probability p, and let x equal x from I equals 1 to I equals n, then x is a binomial random variable, so essentially x is a summation of all of the trials, all of the Bernoulli random variables. And we can write it as binomial NP, where n is the number of trials or the number of random variables, and p is the probability of success. And we can write it as the probability mass function below, n given x, p to the x times 1 minus p to the power of n minus x, for x equals 0 all the way up to n. So let x equal a binomial random variable, then our expected value is equal to np, given by our expected values of all of our Bernoulli variables, and then same thing for variance, where it's our variance of our Bernoulli variables, since it's all summed together n times, it would just be n times our Bernoulli random variable, so it's n times p times 1 minus p. So an example of our binomial random variable. So say the probability of that a patient recovers from a rare blood disease is 0.4. Suppose 15 people are known to have contracted this disease, and we're interested in the probability that at least 7 people survive. So let x denote the number of people out of the 15 who are infected that survive. And we are given that x is a binomial random variable with n equals 15 and p equals 0.4. And so we can calculate our probability using the formula given over here for each value. So we can use a summation for each value of x, and then we can just plug it in. So over here we have n equals 15, so we can put in our 15 here, and then we have our x, so our x goes from 7 to 15, so we have our summation from I equals 7 to 15, and we can use that here. And then we have our probability of success, which is 0.4, and our probability of failure, which is 1 minus 0.4, which is 0.6, and then times to the power of n minus our x. And if we calculate the summation, we'll get 0.390 for the probability that x is greater than or equal to 7. So at least 7 people survive. So multinomial distributions. So a binomial experiment becomes a multinomial experiment if we let each trial have more than 2 possible outcomes. So say if instead of flipping a coin, we roll a dice, we have 6 possible outcomes. We could manufacture products and classify them as being heavy, light, or acceptable. So those are 3 possible outcomes. Or maybe we could draw a card from a deck with replacement and determine which suite the card is in. So that would be 4 possible outcomes. So essentially they're similar to binomial distributions, except they have more than 2 possible outcomes. And then if a given trial can result in k outcomes from E1 to all the way to EK, with probabilities P1, P2, all the way to Pk, then the probability distribution of the random variables x1 all the way to xk, representing the number of occurrences from E1 all the way to EK in n independent trials, is given by the formula below. So essentially this is really similar to our binomial formula, except that we add probabilities for each of the possible outcomes. So in the other one we only had 2 possible outcomes, so we only had P for success and failure, but now we have it for each possible outcome. And our summation from I is from 1 to k is n. So this is our x is our probability distribution. So n would be the number of trials, and p, so all of our probabilities need to add to 1. Yeah. Next, we have geometric distributions. So consider an experiment where properties are the same as those for binomial experiments, where we have identical trials and each trial is independent. Except now that the number of trials aren't fixed. So instead of doing a fixed number of trials, we're doing trials until we get our first success. So our geometric random variable definition is the following. So suppose we repeat independent and identical Bernoulli trials with the probability of p being between 0 and 1, and let x denote the number of the trial on which the first success occurs. Then x is a geometric random variable with the following probability mass function, where f of x equals the probability of success times the probability of failure to the power of x minus 1. So for properties of our geometric random variables, where p is our probability of success, which is between 0 and 1. So our expected value is given by 1 divided by p, and our variance is 1 minus p divided by p squared. And here is an example of using geometric random variables. So say we have a certain manufacturing process, and it's known that on average, 1 in every 100 devices is defective. We are interested in knowing the probability that at least 10 items are found to not be defective before the first defective item is found. So then let x denote the number of items inspected until the first defective item is found. And we are given that x is a geometric random variable with our parameter p, our probability of finding a defective item, is 0.001 or 0.01, and that's our probability of success. And so now we're calculating the probability of x is greater than 10. So that would be 1 minus the probability of x being less than or equal to 10. And then we can use our formula given back here. So our probability of our f of x would be equal to the probability of success times the probability of failure to the power of x minus 1, where x is the number of the trial on which the first success occurs. So here, the trial where our first success occurs, so we want to find at least 10 items, so we can do our summation from our I equals 1 to I equals 10. So we're trying to solve for the probability that our first success occurs before or equal to 10. So x would be equal to 10, and then we're going from 1 to x to calculate the probability of the probability of x equals 0, x equals 1, x equals 2, x equals 3, all the way to x equals 10. So we can just find the summation here from our probability of success, which is 0.01 times our probability of failure, 1 minus 0.01, to the power of I minus 1. So I would start out as 1, and then it would go all the way up to 10. And then when we get the summation, we have our probability of x is less than or equal to 10. And when we solve for this, we get our answer, which is 0.904. we also have negative binomial distributions. So similarly to geometric distributions, we use an experiment where the properties are the same listed for binomial experiments where each trial is identical and independent and follows the Bernoulli rules. And now we also have an unfixed number of trials, but instead of our geometric distribution, which looks for our first success, we're interested in the number of trials needed until the kth success. So instead of the first success, it could be the third success, the fifth success. We can use any number for k. So suppose we repeat identical independent and identical Bernoulli trials with the probability p between 0 and 1, and let x denote the number of the trial in which the kth success occurs, where k is a fixed positive integer. Then x is said to have a negative binomial kp distribution with the probability mass function below x minus 1 choose k minus 1 times the probability of success to the power of k times the probability of failure to x minus k for x equals k, k plus 1, and so on. So some properties of our negative binomial distribution. So our expected value for a negative binomial distribution is k divided by p, and our variance is k times 1 minus p divided by p squared. And this is kind of the sum of k geometric random variables, essentially, since we're basically doing a geometric trial experiment, except we're doing it k times since we're looking for the kth success, which is why our distributions are the same except we multiply it by k. So in our example can be the following. So in a NBA championship series, the team that wins 4 games out of 7 is the winner. Suppose that teams A and B face each other in the championship games, and that team A has a probability 0.55 of winning a game over team B. And so what is the probability that team A will win the series in 6 games? So first we need to figure out what our variables are. So if team A wins the series in 6 games, that would mean that team A needs to win at least 4 of the games, and our x, which will be our trial with the kth success, would be equal to, so our x would be equal to 6, and so we can just plug it into our formula. So x equals 6, so we need to find x minus 1, so that's 5, choose k minus 1, and our k is 4, so k minus 1 is 3, so we have 5, choose 3, probability of success is 0.55, and then that is to the power of k, so our k again is 4, since we need to win 4 out of the 6 games to win, and then we multiply it by the probability of failure, times x, or to the power of x minus k, and our x is 6, our k is 4, so 6 minus 4 is 2, and then we just solve it and we get 0.1853. And that's all that we'll be going over today about common distributions. Yeah, and I hope that this lecture helped you guys, and if you ever have any questions, feel free to reach out. Thank you. Bye.